Good afternoon. It is, in this very special occasion, my pleasure and honor to introduce Dr. Randall W. Poston. He is our school's inaugural Neil Armstrong Distinguished Visiting Fellow. For those of you that are not familiar with the program, you may remember, maybe so you weren't even born then, but you may remember that in 1969 was the first time humanity reached and physically touched the moon. To commemorate that special occasion, and recognize one of our most distinguished alum, Neil Armstrong, the College of Engineering established this recognition. Fellows are selected through a very strict nomination process and evaluation process, and they're all very distinguished individuals. And we're fortunate that the School of Civil Engineering received 2 of those, and you may have already had opportunity to interact with the first one, Professor Rinaldi. But today, Dr. Poston is gracing us with his presence and is going to share his knowledge. I can spend another 5 minutes, 10, 15 talking about Randy, and he wouldn't like that. So let me just say, he is a member of the National Academy of Engineering, and this year became the president of the American Concrete Institute. He has also served as the chair of, those of you that have had concrete already know this document, the 318 Building Code. And he was recognized during a very important task of that committee in the reorganization of the code. And he received, and I'm going to make sure I quote it correctly, the top 25 newsmaker from ENR, and the ACI bestowed on him the Henry L. Kennedy Award for this work. Now it is my pleasure to introduce to you Dr. Randall Poston.
Thank you, Professor Ramirez. A nice introduction, and Professor Young earlier today, this afternoon, for the thing. And also want to thank both the college and the Lyle School for this great honor to be here. Most people that know me, I do a lot in structural concrete, and I'm actually not going to talk about much concrete today. There will be a little bit on concrete, but given our work that I do as a consultant, get involved in a lot of different things over the years, some very interesting things, and I thought this one might be of interest to you. First, I want to just give you a little bit of background about, Pivot Engineers. It's a small firm. We have 13 individuals. Half of them are PhDs, the other half are master's degrees. We're located in Austin, Texas. I've been fortunate over my career to work in most states. I need to work on the upper Midwest here a little bit, as you can tell. Had a few projects outside the continental U.S., including Alaska and Hawaii, and done work in Honduras and in the Caribbean. We're a specialty consulting engineering firm, mainly doing 2 different types of work. One, investigations, looking at structural failures, looking at performance problems with various types of structures, both buildings, bridges, infrastructure of all types, durability, performance problems, and one of my more favorite opportunities in work is actually strengthening and repair design of infrastructure. That's the type of work that I actually enjoy best. In terms of failure investigations, this was a pedestrian bridge collapse in Charlotte Motor Speedway that had, you can see, 114 people were on that bridge when it collapsed. and it was unfortunate. It was all caused by a simple little detail at the precast yard where they filled the plug with chloride-laden grout, and you can imagine what chlorides do to pre-stressing strands. And so on that fateful night, luckily no one was killed, but some seriously injured. I've been involved, got involved with TxDOT a number of years ago. I'm certainly not a vibration specialist, but we got involved in some cable stay bridges. There's two in TxDOT that both had what's referred to as rain vibration issues. And you can imagine when you see something like this, the first thing that comes to mind is fatigue of the pre-stressing strand that makes up the cable stay. And you can kind of see a good, looks like a, as I refer to it, as a wet spaghetti noodle, the technical term. And that mechanism is caused by something that it's hard to imagine, but when it rains and there's a light wind, it forms a rivulet. It's a little stream of water. You can physically see it, and that's enough to create asymmetry when the wind blows, and you get the vibration transfers to the wind. And interestingly, as you probably can figure out, it's only a certain wind. If it winds very heavy, it blows the rivulet off, so you don't get vibration. So it's a very certain set of wind conditions where that occurs. And we designed some dampers to, we had a prototype damper. This is the final installation, which it was a very harsh environment in the Baytown refinery area outside Houston, so it's all stainless steel. And this gives you just kind of an idea of what the effect of that dampers was to reduce the vibration. We recently completed, there's two bridges in Georgia. Both of them experience rain vibrations, been in existence for 20 years, and they're doing the same thing. We're retrofitting it with dampers. This is one of my favorite projects of my career, and is quite old, done back in the mid to late 90s. It's Marina del Rey seawall. It's a very simple structure. It was built in the late 1950s by the Corps of Engineers. It started having corrosion problems along the joint. As you can imagine, in a marina, the water tide fluctuations twice a day ate at the reinforcing steel, creating corrosion problems. They started having collapses of this wall. In the meantime, there's a lot of infrastructure that was, you saw the picture of Marina del Rey. A lot of infrastructure, and interestingly, LA County actually owns the land, and they rent the land to people for long-term leases. We went in with it was very difficult to try to visualize something on the inside because of all the boats. So we went with caissons that are really just vertical bending members and tie rods that were sunk through the back. And we actually did a fair bit of non-destructive testing in order to locate where there was corrosion damage, mainly delaminations on the backside of the wall. We were able to locate those and able to save about $25 million on doing the non-destructive work. We were able to tune or customize each of the wall panels depending on the amount of damage. And this is one of my more recent projects. They went through a major renovation at the Guggenheim Museum in New York City. We were retained as the corrosion consultant for this structure. Of course, Frank Lloyd Wright has a lot of ties to Indiana with his architecture in Bloomington and other cities and towns across Indiana. You can see kind of some of the problems it was having over the 50 plus years that had been in existence. We did some non-destructive testing, figured out where the corrosion was occurring, what we needed to do to mitigate the future corrosion, and it went through a very extensive restoration process. And finally, just a little bit more, this is a 59-story Austonian building in Austin we're working on right now. It has eyebrows and balconies that are about 2 miles long, a concrete slab. A piece of concrete bigger than this came falling off from the 43rd floor, landed on the 10th floor dog park. That's where the residents get to go walk their dogs. They don't want to take them outside. They take them to the terrace on the 10th floor, and a piece of concrete about 60 pounds fell and exploded next to one of the maintenance people for the building. 6 years old when it was first discovered. It's 9 years old now. We went through an extensive investigation and corrosion investigation process. And it was all detail. A reinforcing bar, you can look here, was placed at this edge near a drip edge. And there are no salts anywhere nearby. It was carbonation corrosion, and it occurred within Austin, Texas, very what I consider a very mild environment. So we're in a restoration process, doing 2 miles of concrete slab repair. We're using GFRP bar. It's post-tension in 2 directions, so you have to be very careful when you're removing concrete, as you can imagine, and not disturb the anchored zones. And then we're retrofitting it. We're extending out the slab edge by 2 inches from what it originally was, and using GFRP bars, an inert fiber reinforced plastic. And you can kind of see what the repair looks like once it's finished. So that's kind of a little bit about our background of our company, the type of work we do. This is what I'm going to talk about today. It was the Metropolitan Transit Authority bus terminal maintenance facility in Los Angeles, California. During construction, there was a collapse, and you can see of a large pour of casting of concrete, and the formwork failed and went crashing down. Luckily, there's a couple workers that rode the collapse down. They were not hurt or injured, which was fortunate. And you can kind of, here's a view over the top of this failure. Something like this happens, particularly for a public works project. Certainly a lot happens very quickly, and the contractor who retained us, first of all, they needed to keep moving on the construction, which was kind of our first task. And then in the meantime, we're having to salvage what we can for a collapse investigation in order to figure out what happened, so we make sure we don't repeat it. So we first addressed the collapse and the repair of the damage. They wanted to keep moving forward. We wanted to, there was a question about the adequacy of all this debris fell onto another slab. There was a question about that slab and what its load testing capability was, determine the cause of the collapse. And then we tested the capacity of the actual shoring system, because something came out during our initial investigations that made us think there was an issue. So you can imagine, we'll go through this chart, but once this collapse occurs, we're working in 2 different modes. We're trying to investigate what caused the collapse, how are we going to review it. Work continues. We're having to come up and design repairs, do additional concrete placements. They were up on the 3rd floor of this big facility where these buses are maintained, and so we had to keep moving along the repair process as we were doing the investigation. So there was quite a bit of work that was going on at one time. So another little look at you can see some of the formwork still in place on the shear walls. There was a pour strip that had not been cast, but you can see the amount of reinforcement. It's actually a post-tension slab on top of that, and of course it had not been stressed yet. The cables all ended up having to be removed from the portion that collapsed, but portions that did not collapse, we ended up having to do repairs. So first thing we do is cleaning up things, and usually in a collapse investigation you want to do triage and try to figure out what the heck is happening, what's the element that may have triggered the collapse. Well, you had 16 inches of concrete slab, fresh concrete, that came crashing down on the slab below. And what do? You have to remove it. I mean, there's really not a lot of, things are entombed. You got pieces of the formwork and shoring system that are entombed in this concrete. There's not much you can do about that. So here's condition of one of the columns. You can see it post-tensioned and one direction, and so first things first, we had to come up with some repair details to get that column and the shear wall fixed. So this is after the collapse. This is a portion that part of the collapse placement that we replaced. There's two girders along the edge that are continuous across the construction joint, which we had to deal with. How do we repair that and make sure we can effectively have post-tensioning in those beams? This ramp slab was a previous placement, and for the most part was not damaged during the collapse. So we had various wall repairs, we had a column repair, we had a slab edge repair, and all this debris, this slab here was the one that the owner was worried about that needed to be evaluated because of the collapse. Their concern is, oh, is that one also been affected by the collapse? Came up with a detail. We had, of course, with the columns, coupling the vertical bars. We had to go down, remove all the damaged concrete. Just simply use couplers with headed bars up at the top in order to make sure we could develop the steel. The only thing that we really had to do was a little bit different is we didn't have enough concrete cover by code in order to make it the same size. So you can see at the top of that column it has a little bit bigger dimension in order to make the concrete cover work out. So that was really all the compromise that we had to do in that column repair. Well, you know, so you get thrown out here, and the contractor has, I think he said, 25,000 pieces of this formwork system out there that he's going to continue working on building, and it's like, well, should we be doing that with this particular formwork and shoring system? Well, the answer for us was, for the part that we were going to replace was no. This was the original shoring system. It's aluminum. This is aluminum too. It's a system out of I believe it's either the Netherlands or Sweden, I can't remember, but very, very robust. And you can see all that, you know, as engineers, once you see a failure, we're not going to take any chances. So it was a very robust shoring that we came up to put up under the slab that we needed to replace. Those post-tension beams that straddled along those ramps, we had to basically thread, cut, and couple the post-tension tendons in. Luckily, the beam in the portion that had already been poured in the ramp had intermediate anchors. And so these anchors still had the pre-stressing force. All we really had to do was cut those strands. We had to do it in different locations because you can't put all the couplers in one location. It wouldn't fit. So we just staggered those out in the beams. And you can see kind of the tendons laying there before coupling them and rethreading them to pour the next cast of the beam. So this is they eventually built a cover over the slab. This was all rebuilt, and you see buses operating on it, and no problem. So back to that question about what do we do. The contractor wants to continue because they're renting this formwork system, and you'll see very quickly we knew that there was an issue with some bracing in this system. Not sure exactly what the problem was exactly, but we were fearful that we were going to repeat it. So we wanted to make sure with the bracing, we went out and said, we're going to have to put some additional braces up. The simplest thing for us to do was they got 6x6 pieces of timber and locked those into the aluminum post. And we cut down on in essence, the buckling length of that column. We put those, there was more good lumber wasted on braces. I've never seen such good lumber in my life going in, and they're just saw cutting this thing and just saw cutting in order to put it up. And it's a shame, but it was the quickest and easiest thing for us to do. You can see down here where we supplementing some of the And you'll figure out why we ended up doing this as we go through the rest of the presentation. So we wanted to demonstrate the adequacy of the slab that all this debris came down on. The formwork came down. We told our client, who tried to tell the owner, we can do that using non-destructive testing, and we're quite confident of it. We went and did impact echo testing, and were able to demonstrate that the concrete was solid everywhere. We did not see any concrete in this post-tension slab that even remotely suggested that there was any problem. That wasn't good enough. They wanted us to load test it. So we said we would. So we load tested it. This is the area that we tested after that most of the debris fell on. And we had basically used pools of water. Design live load was 150 PSF, and looking at, we did an ACI load test, which is 85% of 1.2 dead plus 1.6 live. Works out about 36 inches of water. There's our test pools up on top. It's always very difficult to make sure you keep water in the right location. This is underneath. Of course, we're instrumenting. You have to monitor deflections. Once you have to monitor, you have loads going up, you have to monitor deflections. Of course, the shoring isn't there to support any load. It was there just in case something went wrong. So we had the shoring up in place to, if anything were to happen, which we didn't believe would, but you certainly in a load test want to be safe. And this was the load or displacement time response, ACI. It's in the old chapter 20, now in chapter 27. The maximum deflection and the residual deflection, the best we can tell, we've gone through and looked through the literature. There's a new load test procedure that's put out by the 437 committee. Wanted to find out where this was had come from. People went back and looked, and it's like, where the heck is this? The best we can tell is it came from Metasozin. And no one knows where these numbers are or how these coefficients fit or whatever, but we still use it. It still works, and so we ran the load test, and as we anticipated, the structure met the load test and the acceptance criteria, so there was no problem. So now we need to determine the cause of the collapse. That's less important for the contractor, was now moving forward with the repairs and doing what they needed to do, but there's a cost involved. As you can imagine in this, the contractor lost time. Time is money. There was liquidated damages associated with finishing the job on time. All those kinds of things that in real construction projects you've got to be cognizant of. So we need to determine the cause of the collapse. Who's culpable for this? Did the contractor make a mistake? Did the designer make the mistake? Or exactly what happened? So we really could not get very close to the debris. It was not all that safe, but there was a number of places where we could kind of get a hint of what was going on. Here's some photographs, and one of the things you see, of course, is the post of the formwork tower, and you can see it's in a bowed shape, bottom foot encapsulated in concrete. So certainly gave us an idea that there could be some stability, potentially some stability issues. So here's the basic tower frame that goes up. You have your plywood deck. It's supported by these aluminum beams that transfer load over to aluminum stringers. Those stringers load the post, and of course the post delivers the load down to ground. Here's the beam section, and here's the stringer section. You can see they put a little piece of wood up there. That's for nailing the plywood into, for the decking into the system. And the design for that formwork is done based on this design graph provided by the manufacturer of this system. it notes, it doesn't note it on this photograph, but it says you can do up to 3 towers full, 1, 2, or a third one, and still use the same design charts. Factor of safety is 2.5. It says it's based on testing in accordance with CSA, and that's a Canadian standard, apparently, and recommendations of the Shoring Scaffolding Formwork Institute. And they have, so you have various design charts, one for the stringer. Of course, the stringer, you know, they test it, but it's just tested in a machine under basically 4-point bending, as you can see here. And you got a huge, you know, very large capacity. It's never really going to be governed by that, but they have design charts to make sure you can, you know, carry your load from your beams to your stringers, and your stringers can deliver the load to the post. And the thing to note on these posts is there's a screw jack, and those can go anywhere from 18 inches up to 39 inches. 39 inches is about 1 meter, so that's where they came up with. And so you've got the design chart. They vary only because of whether it's a 6-foot frame, a 7-foot frame, or an 8-foot frame. And so they have different capacities. And so what we were able to find in the, you know, through the incredible searching we can do these days of Google, we found an old test frame where this firm company had tested this shoring tower, and this is another picture that we're able to find. And so the interesting thing is how they load the post in this frame. They're essentially have a stiff tower head loading that post, and then that's how they develop the design charts. So the thing, you know, when this is in actuality is kind of the way the frame was tested by the manufacturer of the shoring system. And when you have the stringer up loading across there, you can't just take that stringer and put it on this and say that that's what you get. That's the equivalent load over there. You're not testing the system. You're only testing the tower frame that makes up the system. And there's a big difference that we will see. And most all my steel and colleagues in here knew the answer to this before I ever got to it. But you, with the fact that you put the stringer up there on top of that connection sitting on top, that's a classic stability problem in steel. If you have a girder or beam going over a post and it's not connected directly into the column, you get a destabilizing effect at that location. In essence, that beam or that stringer wants to roll or deflect, and when it does, you actually introduced other forces that the system was not designed for. So this is just another kind of pictorial how it wants to behave, and you can see that wants to, because there's nothing to keep that from laterally moving up there. Again, those are the screw jacks, and they could go all the way up to 39 inches. And this is just kind of a simplistic one way that the manufacturer, if they wanted to put out appropriate design charts, they could go to a simple little model where you put in a hinge and go through some basic statics and determine what the equivalent load is based on developing an equivalent K factor for that particular post. And we did that initially. So instead of having a K of 1 with that hinge in there, for 36 inches you get an equivalent K of 4.8. And you get square the value and all those kinds of KL squared, you're going to be toast pretty quickly. This is very conservative, but it at least gave us a feeling of what the issue was. And then we had to do something a little more formal. This is just the same model looking at how the K factor, equivalent K, varies as a function of that screw jack extension. So, of course, the next thing you do is you want to do a finite element analysis, what everybody does. The big problem there is You don't know what the boundary conditions are. You don't know, is there some rotational restraint when you got those beams going over the stringers? Is there some friction along there with the deck acting as a diaphragm? So depending on what you use for your degrees of freedom, you're going to get we got analysis results anywhere from 30% to 80% of what it was theoretically shown on those design charts. So what do we do as engineers? We want to test it because we don't know. And as this ended up being a several $1 million mistake or issue for somebody, and so we're lucky to have a Bowen laboratory in Austin, which is Ferguson Structural Engineering Laboratory. We asked and our client was good about it. They had another job going on at Stanford University. They're using exactly the same system. So they went in one night, stole a bunch of pieces for us, shipped them by truck down to Austin, and we were able to fabricate those frames. We did 3 tests. We did one similar to what the supplier did. We did then load test 2, where we had just a single frame, and then we did one test with a double frame. So these are the 3 different tests. One, again, where I'll show you how we loaded, made sure we got load directly into there without any rotation. Test 2 included those beams and stringers in the actual system design. Test 3 is with the double system. So here's test 1. You can see we have a box beam that's welded and it's loading directly on that saddle there at the top of the post. So we're making sure there's going to be no rotation, essentially no rotation in that loading head. Test 2 included those beams, aluminum beams, to the stringers. The loads delivered from the stringers to the saddle to the extension part of the post. We actually we had a plywood up there, and we didn't want to pour concrete on that day, but we did, actually this was Mike Englehart's idea. It was really a clever idea. We took a pre-tension concrete slab and cut it through the middle, and then used as part of the loading frame. And the reason he cut it in the middle is so that you got rotation across there, that we could say safely that the slab wasn't contributing to any load distribution in the frame. So they had some precast pre-tension panels out there that they just cut right down the middle. So this is test number 1, and you can see this is the result of the kind of the buckled shape. So that's the first test, which is the one directly applied to the load frame, which was what the manufacturer indicated in his test results. So you have the manufacturer's ultimate data. Here's their allowable. That's the safety factor of 2.5. Our load, we monitored some displacements laterally, what was happening. Don't need to look at those too much, but basically the load got very close to what the manufacturer's data was. The design chart said for ultimate 24.3 kips per leg. The failure load was 23.3 kips per leg, so it was 96% of the manufacturer's ultimate. That's a pretty good test in my mind, certainly for experimental work. So next, we went to the frames where we're now using the system. We got the beams on the stringers on top of the frame. Now all I have to do is find my cursor.
It's over on the right, just go left with it. There, you'll see it.
Oh. Why am I missing it?
It's a little panel.
Yeah.
Oh.
Look at the front screen.
Look at the screen right now. It's on the orange column.
Oh. Why is it not on my screen like that? So, I'm sorry. Thank you. Thanks so much. I appreciate that. Okay, so this is the one-story frame essentially, but with the Well,
There it is. Now click on it and see.
There we go.
notice how much Monster energy drink they've had before. They're hyped up, moving around. Graduate students moving around pretty fast. So we can see Dr. Hellwig walking around there, making sure everybody's safe, got their hard hats on. And so here we go. We start to piece together. Now we see, just by virtue of putting those beams and stringers on, now the load is substantially reduced from what the manufacturer indicates in his design charts. And in fact, the reduction is, we're down to not almost 40% reduction. We're about 62% of the manufacturer's ultimate, and the reduction is about 36% from load test 1, but it's more or less 40%. So the other members, the stringers and beams by the design charts, they're never going to govern this design. It's going to be governed by these shoring towers. Now with the last test, we have a double stack frame. This one's not overly dramatic, like the last one. You can see it bowing. That's it. That's all that happened. You can see, of course, the bow and the tower leg. And if we look at the results for, kind of compare what we showed kind of pictorially, diagrammatically earlier, and you kind of look at how that the stringer is leaning to one side or rotating to some degree from the axis, and so as you can imagine, and this is I think a good, like this picture here really gives you an idea of the curvature that and the buckling that's it's going through, and when we go back and look at the debris field, again, we didn't have a lot to see with the tangled mess, but you saw some posts that looked exactly very similar to what we saw in the those shoring towers. And when we look at that one, they're still in a further reduction. So remember, I said it wasn't shown on the design chart, but you actually it could go, according to their manufacturer's data, up to three levels of the shoring tower and not have any impact on the design charge. Well, we still got a further reduction, another 7%. And again, the other member design forces aren't going to control any of the design of these things. So we have 36% reduction, another 7% reduction, and of course we look back at the safety factor 2.5, and all you engineers are going to tell me, well, why did it fail? It's not at 2.5 yet. It's like, well, when you build things out in the field versus in the laboratory, there's a lot of other eccentricities. There's a lot of there's actually some sway that could happen. This was prevented from sway in this test. You actually could get a little bit of sway. That whole decking system could actually move laterally until the plywood engages into some of the columns. So the fact of the matter is what caused this failure was design charts. The design of this, what happened on this day, they were pouring a 16-inch thick piece of concrete for the slab. That system probably had never been tested for that kind of load before. And typically you're building 7-inch slabs, an 8-inch slab. This bus facility, the amount of load produced by those buses, of course, is quite heavy, much heavier than even probably than a truck loading. And so the design had never really been tested as a system. It had only been tested through those tower frames. So the collapse delayed the contractor, as you can imagine, and we had to move through and design repairs. The load testing confirmed that slab that it collapsed on was fine, did not have to be repaired or removed at all. We only had to deal with the repairs of the collapsed slab. And what we have found out as we started searching through the literature about this, and this is a temporary structure which is not really governed by building codes. You remember the nod that I said there's some Scaffolding and Shoring Formwork Institute. I don't know what that is. It's not a consensus-based organization. It's basically a trade organization, right? That's writing their own procedures for testing these things. And so that detail of having that stringer over the post was really what caused it. Professor Sinha, does that answer your question now? Yes. Yeah, okay. I wanted to make sure I answered your question. So on that day, it was enough to create that instability, that destabilizing effect in that shoring, and it collapsed. So I caution you. We have done a paper. We actually, as an engineer, I felt very strongly about this. I told my client I felt like we needed to share this data and information with the manufacturer, which created all kinds of legal issues, as you can imagine, but they eventually agreed, and we took all the data that we had from our testing and sent it over to them. I don't know if they've done anything about it, but at least I have we have a clear conscience about sharing the data, because it's a safety concern. I mean, these design charts are out there. This is what people are using. Engineers are using for construction engineering, for designing the formwork, and it can be dangerous business, as you can imagine. So that's the completed facility, downtown Los Angeles, and thank you very much.
We have time for questions.
Yeah. Professor Dernovich.
And the placement of the concrete, was this done by pumping or by dropping from the...
They were doing it from a bucket. Yeah, so they had a crane off-site, not off-site, but off the perimeter of the building and just dumping it. And they were moving, that's one thing we checked, were they mounting it up? And, we got pretty good eyewitness accounts that they were moving through that slab in a zigzag fashion in order to make sure they weren't accumulating concrete in a big pile. It's a good question.
Probably had some inertia effects too.
It does. It's not, the buckets are, there can be some, but, we didn't look at a dynamic amplification factor. That's for sure. Santiago.
Thank you very much.
Yes.
Your case is solid. What I find a little bit disturbing is that this system is probably not new. Huh?
Oh, it's old as can be.
And and you anticipated the question. You're saying it had never been pushed to its allowable limit. Huh?
That would be my guess.
That's what.
That would be.
My mind bothers me. An old system like this must be taken to its allowable load all the time. Or maybe not.
I don't. This is really for building construction. I mean, that system. I mean, this was a big building, right? I mean, it's a big parking structure, big slabs, heavy buses, and so in buildings you don't have this type of shoring system. You don't have typically 16-inch thick slabs that you're casting. You're casting 6-inch slabs, 8-inch slabs, 10-inch slabs.
So they then the space
12-inch slabs
further apart.
Yeah, I mean you can I mean it's all got to be designed, but they're that I don't. It's a good question. I don't know. I wasn't not in a position to ask the manufacturer had it ever been tested like that before, but
What are they saying? Sorry. What are they saying?
It was the contractor. It wasn't. They're saying that it wasn't built like the construction engineer had on the drawings, which was not true. I mean, there were some things, as in any. I mean, they pointed out there was some evidence of things here and there where, they needed to add an extra post and they didn't do it, and those sort of things for in between these towers, but it wasn't compelling.
Thank you.
You're welcome.
Yeah, In one of your previous slides, you showed that you recommended cathodic protection for corrosion control.
Yes.
Is that something your company does, or you just recommend?
No, I did not. Actually, that was one, I didn't go into it. That was actually done by another designer. We did all the strengthening of the walls, and then they had a separate cathodic protection designer design that system.
So
Ms. Rob.
you mentioned that if there was one tower, there was a certain capacity. If there were two of them, the same. If there was three, it was the same.
Yes.
Did the manufacturer ever say, and when you go to the failure, is the mode of failure that lowers it, or was it they just limited you up to three? And
They limited it up to 3. I guess they figure, inter-story heights that are never going to be greater than that on whatever you're building. So yeah,
so they never really
they never said what changed. No, they never changed. You saw the old. It obviously was more than one story. I couldn't quite tell whether it was 2 stories or 3 stories that they were testing, but they made it clear in their manufacturer's data that you could take it up to 3 levels and not have any reduction.
How long
Yes,
ago did this happen, Randy?
This happened.
I have a real question.
Yeah, it happened about probably about 3.5 years ago, 4 years ago, maybe.
So you were hired by the,
What's that?
Todd still has that shirt he was wearing.
Well, that's because he never changes.
so you were hired by the contractor.
That's correct.
To keep things going.
Yeah.
And to investigate.
Yeah.
Obviously, this must be in litigation between the shoring manufacturer and the contractor. Is that correct?
It got settled and
It's settled out of court.
it settled out of court, and my client, as far as I know, did not pay any money.
But the shoring company wrote the check, right?
I would assume so. Something. I don't know if they got all the $2 million that they said they lost from time and whatever, but they wrote some sort of check.
No one was injured.
No one was injured, yeah, thankfully, yeah, thankfully.
All right. Before I ask you to join me in thanking Randy one more time, let me just point out that in his appointment, or as part of his appointment, Randy is here for 2 weeks now, and he will return for the next 2 more years after this one and visit Purdue for periods of maybe a month or 2 weeks, for a total of a month in each year. This time, until April 19, Randy is in the 4th floor. Office is 4106, and he told me this. He welcomes your guys stopping by, introducing yourselves, asking questions, see if you can stump him. We'll keep track
It's easy to do.
Yeah. At any rate, it's a good opportunity for you guys to interact with somebody of his experience.
What are the
last,
dates on that, up to the 19th?
I'm sorry? Yes, ma'am.
Week from Friday. It's Good Friday.
Okay.
Yeah, end of the day, Good Friday. Yeah.
Randy, are you aware of Skype? Just run the company through Skype. Stay here. Much easier than going back and forth.
I have heard of Skype. Yes. No, I couldn't. I couldn't go to the XXX and get root beer in Austin. Yeah.
One more thing, the presentation has been taped, and Drew tells me it's going to be available. Where are you going to put it?
We'll post on our YouTube channel.
In the YouTube channel. So, you're welcome to share it with friends, see it again, whatever you want to do. I think there's a lot of good information there. So finally, I'd like to ask you to join me in thanking Randy and welcoming you.